Okay, you have definitely seen these before. They pop up in news articles, in reports, everywhere. These big, intimidating tables packed with numbers and asterisks. Honestly, they look like a secret code, right? Well, today we're going to become code breakers. We are going to completely demystify the regression table and turn it from something confusing into a tool that gives us real clarity. All right, let's dive in.
So, to do this, we're going to solve a mystery. And the central question is a pretty important one. Do women candidates actually get fewer votes than men? Now, it seems like a really straightforward question. And if you just take a quick peek at the data, the answer looks just as straightforward.
And here it is, our first piece of evidence. This is a very simple analysis, basically just looking at the relationship between two things, and only two things. Is the candidate a woman? And what percentage of the vote did she get? The numbers you see here, well, these are our first clues.
And the main clue is, it's just staring us right in the face. A negative 9.877, that's a nearly 10 percentage point penalty. And those three little asterisks, they're basically screaming at us that this finding is super solid, statistically speaking. So, looks like an open and shut case, right? Being a woman candidate means you get way fewer votes. But, in any good detective story, the first clue is never the whole story.
And that brings us to the case of the lurking variables. Because when we're trying to figure out what causes what, especially with data, those first impressions can be incredibly misleading.
You know, our brains love simple stories. For example, it's really easy to assume that getting good grades directly causes you to have higher earnings later in life. X causes Y. A leads to B. It's just a neat, tidy, simple explanation.
But what if there's a hidden character in this story? Some crucial piece of the puzzle that we're just completely missing? What if that simple relationship isn't so simple after all?
And this is where the plot really thickens. Enter the lurking variable. It's something else, let's call it Z, that affects both X and Y. So for our example, maybe something like natural ability affects both your grades and your future earnings. People with higher ability might just be better at school and better at their jobs. And suddenly that clean line from grades to earnings, it starts to look a whole lot fuzzier.
Now, in statistics, this whole problem has a name. It's called omitted variable bias. It's the twist in the story, the distortion that happens when we forget to account for these lurking factors. And let me tell you, it's probably the #1 reason simple analysis can point us in the completely wrong direction.
So, how do we fix this? How do we account for all these other potential explanations that might be lurking around? Well, we need a more powerful tool. We need our high-powered detective's gadget. And that tool is the multiple regression table.
And here it is. This is our full evidence board. See, on the left, in Model 1, that's our initial simple clue. But on the right, in Model 2, we've added in a whole bunch of other suspects, other potential explanations for what's going on. Now, I know it looks complicated, but stick with me. We're going to break it down piece by piece.
Let's start with the most important number in that whole table, the coefficient. The easiest way to think about it is like a statistical lever. It tells you exactly how much the outcome changes when you pull on that one specific lever. And the sign, whether it's positive or negative, tells you which direction the outcome moves. So to put it in plain English, a coefficient lets you make a sentence like this. You can say, a 1-year increase in age is associated with this specific change in ideology. Going back to our table, that negative 9.877 for the woman variable is the coefficient. It's the lever. It's telling us that being a woman is associated with a 9.877 point drop in vote share, at least in that simple model.
Okay, but what about all those little stars, the asterisks? They're shorthand for something called a p-value. But forget the jargon. Just think of it as a confidence meter. The more asterisks you see, the more confident we can be that the effect we're seeing is a real thing and not just some random fluke in the data. So 3 stars, that means we're very, very confident.
Okay, so now we have our tools, we understand coefficients are levers, and asterisks are our confidence meter. We are ready to use this full evidence board to finally solve the mystery. This is the big reveal.
And wow, just look at this. This is the power of digging deeper. On the left, you've got our initial clue, that massive, nearly 10-point disadvantage for women. But on the right, after we account for those lurking variables, the effect shrinks to less than half a percentage point. The story hasn't just changed a little bit, it's completely flipped on its head.
This is the crucial point. Once we control for other important stuff, that huge 10-point gap it pretty much vanishes. What looked like a giant penalty for being a woman was actually just masking other, much more important things that were going on.
So what were these mystery lurking variables? Well, they were things that, when you think about it, have a huge impact on how many votes someone gets. Things like how well the candidate's party is doing in general, whether they're the incumbent running for re-election, how the party did in the last election, and just how competitive the district is. It turns out these factors, not gender, were the real story.
And how can we be so sure that our new, more complicated story is actually better? Well, that's where this number called R² comes in. Think of it as the explanatory power of your model. Our first, simple model, it could only explain about 3% of why vote shares go up or down. It was basically clueless. But our full model, it explains a whopping 87% of it. We have a much, much clearer picture of what's really happening.
But hold on, we're not quite done. There's one final, really crucial lesson in cracking this code. We've got to learn to look beyond just the asterisks and ask an even tougher question. Just because a result is statistically real, does that automatically mean it's important in the real world? Here's a perfect example to explain what I mean. A study found that for every hour boys spent playing video games, they spent 2 minutes less reading. And guess what? The result was statistically significant. It had the asterisks. It was real. But is it substantively meaningful? I mean, is a 2-minute difference really a big deal? Is that something we should be worried about? Probably not.
This idea is called substantive significance, but I just like to call it the so what test. It forces you to step back from the numbers and ask, so what? Is this effect actually big enough to matter in the real world? It's the huge difference between a number in a table and a real-world impact.
And this brings us right back to our mystery. That tiny remaining disadvantage, that 0.45 percentage points, it is statistically significant. The asterisks tell us it's probably a real effect. But now we have to ask, is it substantively significant? Is a gap of less than half a percentage point a major barrier that's holding women back from getting elected? Now that is a much more interesting and complicated question, isn't it? So let's wrap this all up. Here is your official detective's toolkit. 3 simple steps to read any regression table you ever come across. First, check for significance. Look for those asterisks and ask, is this effect even real? Second, check the coefficient. What's its size and direction? And third, and this is the most important one, apply the so what test. Does this actually matter in the real world? And there you have it. You are now officially a code breaker. You have the tools to look past the simple headlines and really question the data for yourself. And that leaves us with one last thought. Now that you can crack the code, what other obvious truths that we all take for granted might turn out to be not so simple after all?